Professor Clements with you. In this example, we're going to determine the magnetic force on a wire that is carrying current. So we have some external magnetic field that is specified. We have a current specified in the wire. We want to know what the interaction is, what's the strength of the magnetic force, and we'll also work on the direction of the force. So we have some things specified. The magnetic field has a certain strength, 4.5 times 10 to the minus 4 Tesla. The magnetic field is to the east. This is a straight wire. It's carrying a current of 1.7 amps, and the length of the straight wire through the region of the constant magnetic field is 3.6 meters. So those are our specifications. So to do just a little sketch of what this might look like, we'd have a magnetic field directed towards the east, and I have a current directed towards the north, and the common assumption would be that both of these are in the horizontal plane. So we have level north for the current and off to the east for a magnetic field, 4.5 times 10 to the minus 4 Teslas, and our current of 1.7 amps, and the length of the wire in this region of magnetic field, 3.6 meters. Well, our calculation for that force is not difficult. We take the current times the length that's in the magnetic field times the strength of the magnetic field. This needs to be a constant for this formula, and we multiply by a factor the sine of the angle between the current and the magnetic field. So let's do this part first. My magnetic field is east, the current is north, they're both horizontal. There's a right angle between east and north, so 90 degrees for the angle, and the sine of 90 degrees evaluates to 1, so we have a factor of 1 for the sine of theta. We only need to concern ourselves with current, length, and magnetic field. We have those values, so let's go ahead and put them in. 1.7 amps. Our length, 3.6 meters. Don't use centimeters, use meters. And then our magnetic field, 4.5 times 10 to the minus 4 Tesla. A little bit stronger than the Earth's magnetic field. And then we'd have a factor of 1, just to remind ourselves that we're not ignoring sine of theta. It's just in this case, the sine of theta produces a factor of 1. So you should pause the video here and do this calculation, see what number you come up with. I came up with 2.75 times 10 to the minus 3 newtons. 2.75 times 10 to the minus 3 newtons. And you might pause again to read the page that I was hiding from you. But that is the magnitude of the force. And a lot of situations, magnetic force is not a huge number. It can be significant, but in especially small mass situations, but not significant here. What about the direction of the force? For the direction, we're going to use the right-hand rule. I'll just abbreviate it, RHR, right-hand rule. And in my version of the right-hand rule, I start with the first vector, and that would be the direction of the current. Secondly, I rotate my wrist and turn my fingers into the direction of the second vector. That would be the magnetic field here. And then my thumb will give me the direction of the force. So I start my fingers, I point my right hand in the direction of the current. I have to rotate my wrist until my palm is facing to the right, to the east, and bend my fingers in the direction of the magnetic field. And when I do that, I find that my thumb is pointed into the paper. The force on this wire is going to be into the paper. Again, right-hand rule, your fingers start in the direction of the current. You rotate your wrist so you can easily bend your fingers in the direction of the magnetic field. Your thumb is perpendicular to your fingers. It points into the page. So relatively easy calculation. Magnetic force on a wire, where we specified the current, the length of the wire, and the strength of the magnetic field, the orientations. So you should practice on that and keep reading.